Wakame seaweed arrives at the factory as wet biomass loaded with salt, sand, and marine microorganisms. And the entire process is built to turn that inconsistent raw material into a food-safe biopolymer film with predictable thickness, strength, and dissolvability. What people call edible plastic here isn't petroleum plastic at all. It's a seaweed-derived hydrocolloid, mainly alginate, engineered into sheets and molded forms that behave like packaging, until you choose to eat it or let it biodegrade. The first engineering challenge is stabilizing the seaweed before it degrades. Fresh wakame can be more than 85% water, and enzymes and microbes start breaking it down immediately. So the plant either processes it the same day or chills it and moves it into rapid pre-treatment. Loads are weighed, lot-coated, and sampled for moisture, ash, and contamination because these values predict how much polymer can be recovered per ton and how hard filtration will be later. Washing is aggressive but controlled. Wakame goes into rotary drum washers and flume channels where countercurrent water flow strips off sand and epiphytes without shredding the fronds into fines that clog filters. Screens and grit traps protect pumps, and conductivity sensors track salinity and wash loops, so the plant doesn't waste fresh water chasing diminishing returns. Some facilities add a brief dilute sanitizer rinse for food contact compliance, then neutralize and rinse again so no residual chemistry interferes with extraction. Next comes size reduction, because extraction efficiency depends on surface area. The seaweed is chopped and fed into wet mills that produce a consistent particle range. Too coarse, and the polymer stays trapped. Too fine, and you create a gelatinous slurry that's difficult to separate. The plant monitors motor load and slurry viscosity in real time because viscosity is an early warning for overmilling and excessive soluble solids release. Before alginate extraction, wakame typically goes through an acid pretreatment. The goal is to convert native salts and remove minerals that would later interfere with polymer purity and film color. This step is run in jacketed reactors with controlled pH and residence time. If the pH is too low or the time too long, the alginate chains can depolymerize, reducing molecular weight and weakening the final film. Extraction is where the factory starts to look like a chemical plant. The seaweed slurry is mixed with an alkaline solution, often sodium carbonate, to solubilize. Alginate is sodium alginate. Temperature, pH, and agitation are controlled tightly because extraction kinetics and polymer chain integrity are a trade-off. Higher temperature speeds yield, but can reduce viscosity by shortening chains. Inline pH probes and viscosity meters keep the process inside a narrow band so the output polymer can be formed into strong, flexible film. Once alginate is in solution, the plant has to separate it from cellulose-like fibers, pigments, and insoluble marine debris. First stage separation uses vibrating screens and rotary strainers to remove coarse solids. Then the line moves into clarification. Decanter, centrifuges, or disc stack centrifuges spin out fine particles. In the plant-tuned centrifuge bowl, speed and feed rate to maximize clarity without shearing the polymer excessively for higher-grade edible packaging. Membrane filtration becomes the key technology. Cross-flow ultrafiltration concentrates alginate while washing out salts, small molecules, and off-odors through diafiltration. Cross-flow matters because the liquid moves tangentially across the membrane, reducing fouling and allowing continuous operation. Pressure and temperature are controlled because a few degrees or a few psi can change flux dramatically. And flux stability determines whether the plant runs smoothly or shuts down for cleaning every hour. Now the purified alginate must be recovered as a usable ingredient. One pathway is precipitation. Calcium chloride converts sodium alginate into insoluble calcium alginate fibers or gels, which are separated, washed, and then converted back or used directly depending on the product design. Another pathway uses alcohol precipitation, where the polymer drops out while impurities stay in solution. It's effective but demands solvent recovery systems, explosion-proof equipment, and distillation energy. Large facilities often choose the route that fits local regulations and energy economics, then run recovery loops to minimize chemical costs per kilogram of polymer. Drying and milling convert the recovered alginate into a standardized powder. Dryers can be belt dryers or fluidized bed systems. They're controlled to avoid overheating that browns the polymer and creates off flavors. Once dry, hammer mills or pin mills grind it to a defined particle size distribution. Because powder consistency controls how fast it hydrates and how uniform the final film solution becomes. The powder is sieved, metal detected, and tested for moisture, viscosity grade, microbiology, and heavy metals. Because edible packaging is held to food standards, not industrial plastic standards, with the polymer standardized. The factory shifts from extraction to film engineering. Alginate powder is blended with plasticizers, commonly glycerol or sorbitol, to prevent brittleness, and often with additional biopolymers like starch, pectin, or agar to tune strength and barrier properties. Mixing is done in high-pressure tanks with vacuum capability because trapped air becomes bubbles. Bubbles become pinholes that leak. The plant controls solids percentage, mixing temperature, and hydration time because alginate takes time to fully dissolve. An incomplete hydration creates gel lumps that tear film and clog slot dies to make bags. The factory needs continuous sheet production, and the main methods are casting or extrusion-style coating. In casting, the alginate solution is delivered to a slot die or knife overroll coater that lays down a metered wet layer onto a moving belt. Wet thickness control is done with precision pumps and gap settings. And inline gauges measure film thickness after drying because a few microns of drift effects, tensile strength, and dissolution rate. Drying is staged in zones. Early zones remove surface water gently to prevent skin formation. Later zones drive moisture down to a tight target, so the film won't block or stick when wound. Alginate films are highly sensitive to water, so the factory often adds a controlled cross-linking step to make the film hold up during handling. That usually means introducing calcium ions to create ionic bridges between polymer chains. Cross-linking can be done by a light spray of calcium solution, a brief dip, or a Tulier co-extrusion where a calcium-containing layer contacts the film. The trick is dosage. Under crosslink, and the film is tacky and weak. Over crosslink, and it becomes stiff, hazy, and slow to dissolve. Once the film is dried and conditioned, it goes to converting. Bags are made by cutting and sealing like conventional plastic, But the sealing physics are different because seaweed films soften with heat and moisture differently than polyethylene. Heat sealers use lower temperatures and tighter dwell time control, sometimes with ultrasonic sealing that bonds without excessive heat. Web tension is carefully managed because biopolymer films can stretch or neck in. So servo-driven unwinders and edge guides keep the roll tracking stable. Cups are a different engineering problem because a cup needs stiffness, shape memory, and leak resistance. One approach is thermoforming. The film is heated to a controlled softening window and formed over molds using vacuum and pressure. Because alginate can reabsorb moisture, the forming room runs with controlled humidity. And the molds are temperature controlled, so the part sets quickly without sticking. Another approach is dip molding, where a mandrel is dipped into alginate solution, withdrawn at a controlled speed to set wall thickness, then cross-linked and dried. Withdrawal speed is a direct thickness control variable. Faster pull yields thinner walls. Slower pull yields thicker, stronger cups. Asterisk water resistance is the hardest requirement for seaweed-based packaging, and modern plants solve it with multi-layer design rather than pretending the material is waterproof. For a cup meant to hold a beverage for minutes rather than hours, controlled cross-linking may be enough. For longer hold times, the factory can apply a thin, edible, hydrophobic coating, like waxes or lipid-based. Layer sprayed or roll-coated onto the formed cup. Coating thickness is measured because too much coating ruins mouthfeel and edibility, while too little allows swelling and softening. Every product type is tuned to a target dissolve profile. Some edible bags are designed to dissolve instantly in hot water for soup bases or seasoning packs, which means minimal cross-linking and a higher plasticizer content for flexibility. Others are designed to survive ambient humidity in retail, which requires lower residual moisture, tighter packaging barriers, and stronger cross-link density. The factory verifies this with standardized dissolution tests, tensile tests, puncture resistance, and water vapor transmission measurements. Because edible is meaningless if it tears on the filling line or turns sticky in a warehouse. Filling and packaging are engineered around moisture control. Seaweed films can absorb moisture from the air, so many facilities package finished bags and cups in high-barrier outer pouches with desiccant, or they run nitrogen flushing to reduce oxidation of any lipid coatings. Checkweighers verify count and net weight. Vision systems check seal integrity and deformation. And lot codes tie every unit back to polymer batches and processing parameters. Sanitation is handled like a hybrid of food, processing, and polymer production. The extraction side deals with wet biomass and high organic load. So clean-in-place systems circulate caustic and sanitizer through reactors, pipes, and membranes at controlled temperatures and flow velocities. Membrane systems require validated cleaning cycles because fouling layers can harbor microbes and reduce flux, which directly reduces throughput. On the film side, hygiene focuses on preventing mold and yeast in humid zones. So air handling, condensation control, and rapid drying are treated as safety measures, not comfort. Waste and utilities are where a seaweed packaging factory proves it can scale. Wash water and extraction effluent carry high dissolved solids and organic load. So plants use screening, dissolved air flotation, and biological treatment. Solid residues, spent seaweed fiber can be pressed and sent to composting, animal feed, or anaerobic digestion for biogas, depending on regional rules. Heat integration is common. Dryer exhaust heat can preheat processed water. And variable frequency drives on fans and pumps reduce power draw when throughput shifts. Reason this process qualifies as high-tech is that it connects marine agriculture to materials. Manufacturing with tight tolerances, the factory uses spectroscopy and viscosity grading to standardize polymer performance, membrane filtration to hit food-grade purity, precision coating to control film thickness in microns, ionic cross-link chemistry to control water behavior, and forming technology to produce shapes that act like plastic without being plastic. What started as slippery seaweed becomes a functional, food-safe package through a chain of controlled separations, controlled chemistry, and controlled drying, because the only way an edible bag or cup works in the real world is if every parameter is engineered, measured, and repeatable.